Hi everyone, welcome to our YouTube channel. In this video, we'll be learning about the different evaluation metrics used in any regression model. And we'll be using this evaluation metrics to gauge the performance of our linear regression model that we built. All right. So there are 5 evaluation metrics, namely MA or mean absolute error, MSE or mean squared error, RMSE or root mean squared error, R2 score, and adjusted R2 score. But even before going to this evaluation metrics, let's first understand what is the error and what are we trying to gauge over here, right? So let us go back to our whiteboard. Now, one thing we have seen over here is if this is my data points, let's say these are my data points. And let's say this is my best fit line. All right. Okay, let me just delete this as well. Let's assume this is my best fit line. And the different points that are present are something like this. Okay, cool. So the issue now over here is how do I figure out if this is my best fit line or let's say or this is my best fit line. Which one? Which one should be treated as my best fit line? So many of you might think, okay, the red line is my best fit line, but we cannot really say like that. Although the red line cuts through 2 points, while the brown colored line cuts through none, it might still be the best fit line. And how do I find the best fit line? The best fit line is the line that has the minimum error. Now, what is an error? So over here that you see, right, this is my line and these are the points. The error is the the shortest distance between the actual prediction. These 3 points are my actual prediction, right? And the prediction by the model. Not actual prediction, sorry, the actual points and the prediction by the model. So this is the error. Again, here, this is my error. This is my error again. All are perpendicular lines. So we drop a perpendicular line from the actual point to the predicted point. All right. Let's call these points as D1, this as D2, and this as D3. Now our total error is a function of all these points, D1 plus D2 plus D3. Or let's not just call plus because it's just a function of these 3 points, right? So it's a function of D1, comma D2, comma D3. The function can be anything, right? All of them plus, squared plus, or whatever it is. So the error is a function of all the D's, right? Now this error needs to be minimized. Whichever line has the minimum error will be termed as the best fit line. All right. So the evaluation metrics that we saw just a few minutes back were ways to optimize the error. Not optimize the error, but to output the error. Okay. The very first thing we learned was MAE. That is mean absolute error. So what is mean absolute error? Let's see the formula first. So this is nothing y actual minus y predicted. What is this I? I means I'll be iterating over all the points. So actual minus this is nothing but actual, and this is nothing but the predicted. So actual minus predicted value, and I'll take a absolute value of this subtraction. And since I have taken I, so I must run through a loop. So I equals to 1 to n. So for all the points, repeat the same thing. Actual value minus the predicted value for I equals to 1, for I equals to 2, dot, 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 for I equals to n, right? Now, since it's the mean absolute error, this is what I got as a absolute error. But since it's a mean absolute error, what we also need to do is we need to multiply it with 1 by n or divide it by n in simple words to find the mean. Got it? So this is my mean absolute error. Now, where is it important? First thing, it is easy to interpret. It is less sensitive to outliers. So whenever you see you have too much outliers and you want to absolutely remove the outliers, then MA is not something you would want to go with. If you want to keep those outliers, then MA is probably one of the metrics you would want to use to gauge the performance of your model because it is less sensitive to outliers. The metrics, the output, the error unit is in the same unit of that of the target. Why did I even mention the unit of error is in the same unit as that of the target? Because next, what we had was MSE or mean squared error. Now, the formula for mean squared error is very simple. The same thing, yi minus y predicted, that is actual minus predicted value, but we simplify the square of it. Again, I equals to 1 to n and divided by 1 by n. I mean, multiply it with 1 by n. So instead of finding the absolute difference, we find the square of the difference. This is what we call as the mean squared error. Now, what happens in mean squared error is it penalizes the larger errors heavily because we are taking a squared term. It is more sensitive to outliers. So whenever you want to get rid of the outliers, you must want to use MSE. Whenever outliers is a big issue, then you would want to go with MSE. Here, the matrix is not in the same unit as that of the target because we are doing a square. While for mean absolute error, the error term is in the same unit as that of the target. For mean squared error, the error terms is in the squared unit of that of the target. Now to get over it, we came up with another term which is the root mean squared error, which is nothing but square root of mean squared error. So all of this same, just square rooting it. Now how this is useful? This penalizes larger errors heavily, but less obviously compared to mean squared error. And the output, the error is in the same unit as that of the target. So there is no issue with respect to unit confusion, right? But it still penalizes the larger errors heavily, or it is also sensitive to outliers, right? So this was all about MAE, MSE, and RMSE, that is root mean squared error. We just clear everything out. Okay. So what next we have is the R2 score, which is a very important metric. All right. So we have R2 score. Now, what is R2 score? It explains the variability of a model, how much the model varies. It is also called the coefficient of determination, right? So for example, let's say I have got an R2 score of 0.72. It means that the model can explain 72% variability in the dependent variable. right? It means the model can explain 72% for the dependent variability for the dependent variables. The formula for R2 score is, which is not very important for you to remember, other than for interview perspective, because you know scikit-learn itself gives us the R2 score. But if you want to know it, it's 1 minus RSS by TSS. What is RSS? RSS means residual sum of squares. It's written as summation of yi minus y predicted. And TSS stands for total sum of squares. Which is yi minus y mean whole square. So basically what R2 score is, it explains how better a model is with respect to a simple mean model, right? Let's say you have typically, let's say what we did was area and price. So you have several areas and you have several prices, and I give you an alien area. Okay, and you need to predict the price. What you can also do is you just find the mean of all the price and put it over here. One of the ways to treat missing values, right? You can do that. For example, you have area as 2 and here 2, 3, 3. And I ask you what would be the value of 4. You can say, okay, I'll take 2 plus 3 by 2. So 2.5. So here I'll put 2.5. Even if I say the area is 10, you will still say 2.5, right? Because that is the average. So this is a mean model, which is not a very good model. What R2 score does is it tells you how better your model is compared to a mean model, right? If a model were only to predict the mean value, that is find the mean value, keeping that as a base model, how better is your model, right? So whenever the R2 score is 1, so if R2 score is 1, it means perfect prediction. If R2 score is 0, it means it is no better than a mean model. So it is basically similar to a mean model. R2 score of 0.72 means it is, or any value means it is that much percent. It can show the variability by that much percent. But what do I mean when I say R2 value of minus negative, minus something, less than 0? That means it is worse model than the mean model. That is worse than mean model. That is, even if you do nothing, simple mean model, your performance would be better than the model that you have developed if your R2 score goes in negative, right? So this is very, very important. And this is something you should always remember from the formula. That R2 score gives you or tells you how better your model is with respect to the mean model. Now, can we think that the R2 score keeps on increasing if we keep on adding more number of columns? So let's say the prediction that the model would give with only area will always be poor compared to what a model would give you as a prediction if you had multiple number of features. For example, area, number of rooms, number of kitchens, stories, so on and so forth. Can I not say that? So if we keep on increasing the number of features, the R2 score will keep on increasing or at least be stagnant. It won't decrease because the R2 score it would get by keeping area only as the column would still be the answer, right? It can only increase if you increase the number of columns. So R2 score does not check us if we are, including random columns, useless columns. For example, in predicting house prices, how many rockets landed on moon doesn't really matter. Or who is the president of North America or America, USA, doesn't really change the house prices. Not typically, right? So these are useless columns, useless features, which would only increase the computation power of the model. And we do not want those features. So instead of using R2 score, we use something called as an adjusted R2 score. Now, what is an adjusted R2 score? Let me quickly remove this. All right. So we know what is R2 score, and let us also understand what is adjusted R2 score. So adjusted R2 score penalizes the model for adding features that do not improve the model significantly. The formula for adjusted R2 score is 1 minus 1 minus R2 score into n minus 1 divided by n minus p minus 1. What it means is R here refers to the R2 score. Okay. N here refers to the number of rows. That is the total data points, the total number of rows that it has as a data. And P over here refers to the number of features. That is the number of columns. So you see P goes in the denominator. So if the number of features keep on increasing, the value ultimately keeps on decreasing. So adjusted R2 score penalizes the model if you keep features that do not improve the model by much. Right? So instead of usually using R2 score, we tend to use adjusted R2 score. All right. So now that we have learned the theory about all these features, all these evaluation metrics, let's see how to use them in our pre-built linear regression model. Okay, so AMAE. Let's quickly import all this from the scikit-learn library. So I'll say uh, from sklearn import mean absolute error, mean squared error, and R2 score. Okay, fine. Now let's check how these parameters actually gauge our model, right? Um, let's just quickly restart and run all our. Once this is run, we can simply check our model. All right. Mean absolute error is an issue. All right. How come? Not import mean absolute error. Absolute. Is the spelling is all correct? Yeah, I think from sklearn.metrics is why it's creating the problem. Yeah, now it's fine. So from sklearn.metrics, import mean absolute error, mean squared error, and R2 score. Now let's check for all of them. So MAE. What I'll do is I'll just copy this mean absolute error of. So error between what? Our predictions and the actual values. What is our prediction? That is stored as predictions, right? These are our predictions. And between predicted value and the actual value, which is the y test. So this is our mean absolute error. All right. We can find the same for mean squared error. Now, mean absolute error, mean square error, or RMSE values needs to be decreased, while R2 score and adjusted R2 score needs to be increased. So for mean squared error, I'll take mean squared error, same thing. Okay. I can also find for the RMSE value. Now, RMSE actually doesn't exist, right? If you can see, I've also not imported anything called as RMSE. So what we need to do is we need to find the square root of mean squared error. So what I'll say is np dot square root of mean squared error. So simply the square root version of it. So these are my errors, which is not very good. I mean, it has a huge amount of error, which looks pretty bad. But let's go ahead and try to find the R2 score, right? So I'll say R2 score. So here I'll say R2 score of predictions and y test. Okay, so it gives me a negative value. That is, it says your model is even poorer, even poorer than a mean model. So you need to change your model immediately. Cool. That's totally fine. Here we are not trying to get the best model. We are just trying to understand linear regression, and I hope we have understood how linear regression actually works. It might not be the best model for this data set. And that is exactly the case. That's why we have so many models, right? To understand. And we could also see how our model is with respect to the data points. It is not even catching most of the data points, right? So that's totally fine. Okay. Now finally the adjusted R2 score. What is the formula? The formula is 1 minus, right? 1 minus R2 score into n minus 1 whole should be in bracket divided by n minus p minus 1, right? So this is our adjusted R2 score. All right. So we already have our R2 score as, let's just keep it as R2. All right. So what I want to do is I want to find n. So what is n? N equals to the number of rows. So len of x test is what we can do, right? This is our n. What is our p? P is the number of columns. So what we can do is shape of 1, right? So x dot. Why am I taking x and not x test? Because x test doesn't have a shape because it's a numpy array. And both x and x test will have the same number of columns, right? So x shape of 1. All right. And R2 we already know. This is our R2. Okay. In that case, we do not need this. That's fine. So we have found everything. Now simply, let's just use the formula. So adjusted R2 equals to, let's just copy the formula. So 1 minus R2, right, into n minus 1 divided by n minus p minus 1, right? And we also have to call it, forgot to call it. So this is the adjusted R2 that we get. So adjusted R2 is even negative, right? So what it says is also not all the columns that you have, not all the features that you have is good enough. So area is not perhaps one of the best features that you have. Again, when we do it with just one feature, adjusted R2 score is not really helpful. We'll understand that when we work with multiple features, which is what we'll be learning in the next lecture with multilinear regression. Right? See you in the next lecture. Thank you.